Welcome back to this new lesson of algorithmic design. During the last lesson we introduced the single source shortest path problem, and we tried to solve it by observing that BFS basically solves a very same problem on unweighted graph. Now let me go back to the last slide we were dealing with. So this is the situation for BFS. In BFS we have black, gray and white nodes, and we have a queue which is meant to store the gray nodes, and from these gray nodes we move on trying to extending all the path from them to new nodes, to undiscovered nodes. And to do it we decided to take the first node in the queue, which is the node having the smallest distance from the source. Now let me go to the slides. Here we are. Now this operation doesn't work, and the point is that we cannot guarantee that the smallest path from the first node in the queue is the smallest path can be achieved all along the graph from this situation. And as you can see here, for instance, moving from the node number 2, I end up in 6, and this is done by crossing an edge whose weight is 15. So if I decide to go on with this strategy, I end up in labeling 8 with a number which is 16, which of course is not the correct number, because we know that we can reach 6 by going through this path with just 11 steps, let's say, okay, with a path having a length 11. So the idea is to change in some sense the perspective, and instead of having a queue labeling gray node, having a queue storing all the white nodes in the graph, and this node should be in some sense pre-labeled. So while once you've selected you gray color a node in BFS, you end up with setting is distance once for all. In this case we assume that the white node hasn't finished, and so their distance may change along the computation. And in doing it we need to of course pre-label all the possible candidates to be reached from the source. So the situation moved from this slide, which is the BFS, a kind of representation of BFS computation, to these slides. Here we basically have already computed the distance of 2 and 3 from 1, and of course of 1 itself. And we are still trying to compute the distances and the paths of all the nodes, white nodes, of course. So the queue right now is no more the queue of the nodes on the boundary, let's say, of the reachability, but is a queue of all the undiscovered node, yet undiscovered node. And oh, by the way, send me an acknowledgement that you can see me and hear me, which is much better. Now the point is, so the black nodes, so the nodes that you can see depicted in black in my slides are already finished. So their distance and the path to reach them are being already computed. So now we want to compute all the path for and the distances for all the white nodes. So how can we do it? Well, we can observe that if we take the nodes whose distance, labeled distance is the shortest one, so the let's say candidate distance is the smallest one among the white nodes, of course, well, for sure that distance cannot be decreased by passing through the other nodes. So I cannot decrease the distance 7 by passing through 6 or 5, simply because this is the smallest distance among the white nodes. So for sure, since this distance, candidate distance, has been computed starting from the black nodes, this is the right distance for 4. Okay, so I cannot decrease it by moving along 6 or 5, and this is the smallest distance moving passing by the black nodes. So this is the correct distance, the exact distance of 4 from 1. So the idea is to extract from the queue of the already unfinished node the one which has the smallest candidate distance among the others, of course, and to finish it. So we select in this case the smallest, the node whose candidate distance is the smallest among the white nodes is 7. So we extract it 7 from the queue. We black labeled it, saying this is the final distance for it. Of course, we update the path to reach it, and that's why we colored this node by using a different color, and we can update all the white nodes reachable from it. Or better, we can update all the candidate distance for the white nodes directly reachable from it. In this case, since the distance of 4 is 7, moving along this edge, we can reach 5. So we can update the candidate distance of 5 by saying this is 8, which is 7 plus 1. Moreover, we can update in some sense a candidate predecessor for 5. So that's why this is we have this different color, saying this is a 4 is the, let's say, candidate predecessor of 5 in the shortest path from 1 to 5, but we don't know yet if it is the final one, because this node is still in the queue and this node is still white. Okay, so this strategy, this algorithm, let's say, is known as Dijkstra algorithm, from the name of the guy who invented it, and it works exactly as you saw it. So again, here we have a queue containing the node 6 and 5. From the queue we select the node having the smallest candidate distance among the two, which is 5, and so we extract it from the queue, we finalize it, meaning we know for sure that this is the correct distance for 5, so we also finalize the predecessor of 5, and we may try to update 6 according to the fact that the path moving through 5 is shorter than the path moving through 2. So in this sense, so now the path moving to 6 going through 5 takes as length 8 plus 3, which is 11, which is smaller than 16. So we have to decide whether the best path is going through 2 or is going through 5, and of course is the latter one. The latter is the better solution, and so we update. We should update the candidate distance of 6 as the distance from 2 to 8 plus 3. Okay, and according to this update, we will also update the predecessor link, and this is This is why this color has been decolored, this edge has been decolored, and this edge has been colored. Okay, so this color means, look, I'm seeing, I know that the predecessor of 6 in the shortest path from 1 is 5. And that's all. Okay, really simple, really similar to BFS. Of course, you may also use this strategy to solve to compute the shortest path for unweighted graphs, but you will see. I mean, there will be an extra cost due to the fact that we are playing with let's say what is right now a priority queue. Okay. So let me do some observation, some notice about the Dijkstra algorithm. So what was as I just said, what was a queue in BFS now has become a priority queue with respect to candidate distance. Why? Because we have this queue containing all the elements in the queue itself, and we at each extraction we always select the one having the minimal candidate distance. So right now this is a priority queue. Moreover, the Dijkstra algorithm does not need coloring, because I mean, moving from the queue of BFS to the priority queue, we basically avoid the need of the gray coloring. Moreover, we can distinguish between white nodes and black nodes simply by observing that all the white nodes are in the queue and all the black nodes are outside the queue. So coloring is not really needed. So, moreover, the paths to reach a node is treated as distances. So every time we update candidate distances, we need to update also the predecessor. Okay, and moreover, and final, and I think really important, this is I mean a kind of algorithm. It's not really an algorithm, meaning that it does not specify how to handle the queue, or better, the priority queue. We know that we have always to extract the minimum. We know that we have to handle many different nodes, but we don't know. We know that we have to update all the elements in the queue according to the candidate updates, but we don't know. I mean, the algorithm itself does not specify how to do it. So this is a kind of meta algorithm, saying that the complexity of the algorithm will depend on the complexity of the operation, and since we have not specified how to handle the queue, I mean, we have not specified which data structure we are going to use to handle the queue, the complexity may depend on it. Okay. Now, is this enough? I mean, are there any limitation in the usage of Dijkstra algorithm? Well, actually, there is a limitation, and it is due to the fact that we always assume to build up the smallest path, to extend the smallest path by taking into account the smallest path reaching a white node up to that up to a certain moment. Okay, and I mean, it could be the case that this is not a good strategy if you are dealing with negative weights. So let's have a look to this small graph to clarify why black weights are not welcome in the by Dijkstra algorithm. So, or better, are not properly handled by Dijkstra algorithm. But well, let's take into account this situation. We have we have already performed most of the computation, and we already finished the source, which is 1, the node number 2, and so we have updated the candidate distance of the queue for 3 and 4 according to the edge moving along these two nodes. Now, by extracting the minimum among the white nodes on the priority queue, I end up in deciding that the best way to reach 2, by extracting the minimum, I'm extracting 2, of course, and once I've extracted it, I need to finalize it according to the Dijkstra algorithm. However, so the distance to reach 4 would be 2 according to the Dijkstra algorithm. However, as you see here, I can reach 4 by going through this path, so the path moving along 3, simply because, and this is the smallest one, simply because from 3 to 4 I have a negative edge, and so the path 1, 3, 4 has length 0, which is less than 2, which is the length of the path moving along 2. So this is due to the fact that the Dijkstra algorithm assumes that all the edge has a non-negative distance, and non-negative weights. Okay, and so this could be a limitation. However, it should be also noticed that if you have cyclic graphs, adding the chance of placing a negative weights on an edge give you a kind of wrong definition for path lengths, because let's assume you have a cycle in whose length is negative, and this cycle is along the path moving from your source and the destination you want to reach. Then you don't have any smallest path, shortest path. You don't have any shortest path, because for any length of the path you can simply keep looping on the loop, decreasing the length of the path, since the loop has a negative length, until you reach the length you want to reach. And so if you allow a graph to have negative weights, you don't have a proper definition of shortest path. I mean, it really depends on the topology of the graph itself. If the graph is not cyclic, or if you don't have any cycle having negative length, then you may define, you can define the shortest path, otherwise it's not possible. Okay, so this limitation is not really a limitation, an important limitation from certain point of view. Okay, however, it's important to notice that you cannot apply the Dijkstra algorithm on a graph having negative weights. Now let's have a really quick overview of the pseudocode related to the Dijkstra algorithm. Of course, we have an initialization step, or better, an initialization function, in which procedure in which basically every candidate distance, again we use the property d of the node to represent the candidate distance, and both the candidate distance and the distance itself. At the beginning, all the candidate distances are set to infinity, and all the, as did for instance in BFS, for instance, and all the predecessor are set to nil, exactly as BFS did. After that, well, we are missing, of course, from the BFS procedure, we are missing the coloring, but as I said, Dijkstra algorithm does not need coloring. Now, let me leave for a while this function alone, and let's move to the main Dijkstra algorithm. So the Dijkstra algorithm basically initializes, init the graph by performing all the operation we saw before. It set the distance from the source of the source node to 0, of course. After that, it built the queue of all the nodes. So while the queue is not empty, so this is of course a priority queue. While the queue is not empty, the first step to do is to extract the minimum among all the nodes. And once this minimum has been extracted, this is of course the node having, so this node has been finalized in some sense. So the distance is set, its distance has been set once for all, forever. So it cannot change anymore, the distance of u. Now, from this node, I can try to update all the candidate distance for the nodes which are still in the queue. So to do it, I can try to, well, first of all, I need to go through all the neighborhoods of u, and as you may remember, in the adjacency list of u, right now I have not only the destination node but also the weight of the graph of the edge going from u to v. So once I've got these triples, this triple, which is basically a representation of the edge moving from u to v, whose weight is w, I can try to relax the candidate distance, to update the candidate distance of v and the predecessor of v by moving along u. So now v for sure have a candidate distance and a predecessor, which can be of course infinity and nil respectively. And now I've reached u, I finalized u, so I know the distance of u from the source, and I can try to update the corresponding distance on v, depending on whether the new path moving along the edge uv is smaller or not, to the smaller in sense, meaning as a length smaller with respect to the candidate distance of v. And this can be done by the relax function, of the relax procedure, which basically tests whether the candidate distance of v is greater than the distance which is right now, since we have just finalized d, is the distance from the source to u plus the edge moving along u and v. If this is the case, then we can update the distance of v on the queue, okay, and the new candidate distance for v should be the distance of u from the source plus the edge w. And so this is meant to update the distance and update the data structure queue, which is a priority queue. Now once this is done, of course we have also to update the predecessor of v on u, meaning that we have discovered a path, a shortest path moving from the source, well, a shortest with respect to the previous candidate, let's say, a shortest path moving from the source to v, and the last edge is the edge moving from u to v. Okay, this is it. Now let's try to evaluate the complexity of this procedure. Well, at the very beginning of the computation, all the nodes should be placed in the queue. So as soon as one node is extracted from the queue, and this occurs at each while loop, the node is finalized, so never enter back in the queue anymore. and there is a for loop which iterates over the adjacency list of U. So as we saw on BFS, this basically means that the for loop iteration in the total, so in the globally, in the total number of steps performed by the algorithm, cost as much as the cardinality of E, okay? Because we are for each nodes in the queue, we are extracting, we are considering all the neighborhood of that node, and all at the beginning of computation, all the nodes of the graph are in the queue. So since at each while loop we are extracting one nodes, we end up in performing the loop a number of times, which is exactly the number of edges in the graph. Okay. So the overall cost of Dijkstra algorithm is the following one, the one you can see on the slide. Let me see. Yeah, you can see it. So the theta of cardinality of V, which is the initialization part, plus the cost of building the new priority queue over a set of elements, which is the length of the cardinality of V, of course. So we need to place all the nodes in the priority queue, all the nodes of the graph in the priority queue. So this operation takes something which depends on the data structure we are working on, of course. And that's why I'm not explicitly saying what's the complexity of this operation. Okay, I don't know how to evaluate the complexity of building the priority queue, simply because I don't know how from the algorithm I don't know how the priority queue is handled. Okay, and we will see how this operation may take different time according to the data structure that we are going to use. Once we have built the priority queue, we need, of course, to extract for each while loop. Remember, while loop is performed once for each iteration of while loops. Well, the iteration of the while loops occur once per nodes in the graph. So the number of time I'm repeating the while loop is the number of basically nodes in the graph itself, because I'm keeping extracting elements from the queue. So the complexity of the while loops is the number of time I'm repeating it, which is the cardinality of the nodes in the while loop, multiplied by the cost of extracting the minimum. And I mean, this is upper bounded for sure by the cost of extracting the minimum on the full queue. Okay, so this is an upper bound, let's say, in some sense. Now this is the cost of the while loop, where we are missing the cost of the for loop, which is represented by the last terms of our addition. And again, the number of time I'm performing the block associated to the for loop is equivalent to the number of edges in my graph, and that's why here we have a cardinality of the multiplicator, multiplied by what? By the cost of updating the distances. So every time we discover a new path, a new smaller path, we need to update that value. We need to update the candidate distance on the queue, so we need in some sense to update the data structure. Well, not in some sense, we need to update the data structure in our which represent the white nodes. So in the worst case scenario, this operation for sure depends on the number. Well, in general, this operation depends on the number of elements in the queue, but for sure is upper bounded for each of these steps. Is upper bounded by the number of by the cardinality well, this operation is bounded by the application, the cost of performing this operation on the queue, on the full queue, so on the queue containing all the nodes in the graph. Okay, and this is the overall cost of the Dijkstra algorithm. Now let's try to see what's the real cost when we use a specific data structure. So this is a general cost which unravels the fact that the Dijkstra algorithm is a kind of meta algorithm because we don't know which data structure we are using to full finish our operation. Now let's see what's going on if we use arrays, for instance, to store our priority queue. Well, building an array, of course, building an array takes time, theta of the cardinality of the length of the array we want to build, because we have to initialize it. So for sure takes time, theta of n, where n is the size, is the number of vertices in our graph. What about extracting an element from the queue? So extracting an element from the queue, if we represent the queue by using an array, is simply going through the array, searching for the nodes having the smallest candidate distance, and then placing it at the end of the array by swapping the final element in the array and the element having the smallest candidate on the array. So this takes time equivalent to going through all the array, which is theta of n again. So what about updating a value in an array? So we want to update the candidate distance. Our goal by using update distances is, of course, updating the candidate distances. If we are using an array, updating a candidate distance, once you know the index of the node you want to deal with, is simply theta 1, because you go to that element in the array and you simply update the value. So if we perform all this operation, we take to understand and we try to understand the overall complexity of Dijkstra algorithm, then it turns out that by using array we have a complexity which is theta of cardinality of v squared plus cardinality of v. Okay. Now, what if we use a different data structure? Well, you probably have already guessed that we are dealing with priority queue and we are searching for minimal value on the priority queue. So what's a good data structure to deal with all these operations? Binary heap. Okay, a binary heap is a perfect data structure to handle all this operation, because we know how to build it, we know how to extract the minimum element on the data structure, and we know how to update and better decrease a key on a binary heap, which is exactly what is done by the Dijkstra algorithm. So the complexity of building the binary heap, of course, is theta of n. We already saw it, why. The complexity of extracting the minimum element on the binary heap, is of course big O of log n, because the minimum is the element on the root, and you simply have to call ep5, replace the element on the root with one of the leaves, well, the rightmost leaf, and then call ep5, which takes time, big O of log n. And what about updating an element, a key? So what about updating a value, or better decreasing a value, which is exactly what Dijkstra algorithm does? Well, again, this can be done in time, big O of log n. So the overall cost of performing the Dijkstra algorithm by using binary heaps as data structure to represent the priority queue is big O of the sum between cardinality of V and cardinality of E multiplied the logarithm by the logarithm of cardinality of V, which is smaller. I mean, if you are dealing with sparse graph, is much better than the previous solution, of course. It is worst in the case of a dense graph. So if you have a dense graph, the best choice is to use the arrays. However, if you are dealing with a sparse graph, so the number of edges is not that important with respect to the number of the square of this number of nodes, this is a pretty good solution. Okay. Now, we haven't seen it. However, I mentioned that there is another kind of data structure, a binary, well, another kind of heaps named Fibonacci heaps. We haven't seen it, but you can find it online or on the book we are using as reference. And this data structure is able to perform extraction and building in the time as being reached by binary heap, but moreover is also able to update, so to decrease a value in constant time. This is, I mean, not for the single operation, but is globally. So if you have an operation to perform over the Fibonacci heap, and some of them are extractions, some of them are updates, and so on and so forward. Globally, the cost of all the update operation takes time theta of 1, so they are constant. In this case, so by using Fibonacci heap, we are able to perform the Dijkstra algorithm in a time which is much better than the Fibonacci heap case, and also better than the array case. So of course this data structure performed very well, but from the asymptotic point of view, but has some drawbacks in terms of constants. So it really depends on the graph you are dealing with. You may use arrays, binary heaps, or Fibonacci heap. Okay. That's all. I hope you enjoyed the Dijkstra algorithm. I mean, it's one of the most famous algorithm of the algorithmic design, and probably one of the most used. And we will see by the end of the lesson probably why. Now let's move to a different. So right now we are able to solve the single source shortest path problem for a graph which does not have negative weights. Okay, I mean, there are other algorithms dealing with negative weights, but we are not going to see them. We are going to move to a different kind of problem, which is all pair shortest paths. As you may have already understood, this problem is different from the single source shortest path problem, because in this problem we want to compute the shortest path between all the pairs of nodes. So we don't have a single source, but we want to, let's say, deal with all the possible nodes in the graph. So how can we solve the problem? Well, the most naive strategy is to use the Dijkstra algorithm and reiterate the Dijkstra algorithm nth time according to cardinality of V time. So for each node, we select that node in the graph. We select that node as the source of the Dijkstra algorithm, and we keep repeating the Dijkstra algorithm as soon as we compute all the shortest path on the graph. Okay. However, this strategy, as already unraveled, is not able to deal with negative edges. Okay. Moreover, it has a computational cost which is relevant in the case of dense graph, as you may figure out by looking at this table. Okay. Now let's try to figure out a way to solve the all pairs shortest path problem in a nice way. So let's try to simplify in some sense. It's not really a simplification, I mean, it's just a way to see the things which allow us to understand better what's going on. So if we have a graph dealing whose nodes are natural number, we may say that between the natural number A and the natural number J there is a shortest path for sure. Okay, if of course I can go from I to J, so if J is reachable from I, there should be a shortest path among the two, and let be P built up in this way, the shortest path between these two numbers. Okay, now and let's assume that K is the greatest internal node in the path. And that's why I was saying let's assume that the graph is a graph whose nodes are natural number, because what's the meaning of greatest if you are dealing with graph which is not dealing with natural numbers? Okay, so the situation is the following one. We have two nodes. We have a path which is the shortest path among the two nodes, and K is the greatest internal node in the path. So apart from I and J, which we don't know what they are, we for sure all the nodes involved in the path are smaller than K apart from K itself. Okay, so if this is the case, for sure there exists an index such that the edge just before that index and the edge corresponding to that index have K as destination and source respectively. So this the source of this node, well, the destination of this node is K and the source of this node is K. Okay, and these two, not node but edges, of course, the destination of this edge is K and the destination of this edge is, and the source of this edge is K. And these two edges belongs to the path, the shortest path going from I to K, to J. Okay? So, if this is the case, we also know, since this is the shortest path, we also know that this prefix of the shortest path should be a shortest path too from I to K. Because if this is not the case, we can replace it by using the shortest path between I and K and ending up with a path which should be shorter than the shortest path from I to J. Okay? So the prefix of the shortest path from I to J should be the shortest path between I and K. Of course, the very same thing also for the last part of the shortest path. So the path going from E over bar H and H should be the shortest path between K and J. Okay? So right now we have reduced the problem of computing the shortest path from I to J as the problem of computing the shortest path from I to K and the problem of computing the shortest path from K to J. Okay? And remember, K is the greatest internal nodes in the path from I to J. So all the nodes belonging to 1 to over cap J minus 1. So in the first part of the path, all the nodes involved in all the internal nodes in the first part of the path should be smaller than K. And again, also for the last part of the path, all the internal nodes should be smaller than K. Okay? So a possible idea is to exploit this observation to compute the shortest path and reduce the problem of computing the shortest path between I and j to the problem of computing the shortest path to I, k, and the shortest path from k to j. And this is basically the intuition of the Floyd-Warshall algorithm, which iteratively build up different matrices containing the distance among between nodes. So if this matrix contains the length of the shortest path whose internal nodes are smaller than k, okay, then we can compute the matrix containing the length of the shortest path whose internal nodes are smaller or equal to k by using this equation. So either the smallest path between I and j does not contain k, and this is the case, or by allowing a path moving through k, we are able to find a shorter path. And so in that case, the shorter path we have just discovered by allowing k, which is the value we need to insert into the matrix, into position ij of the matrix dk, is the sum between the shortest path between I and k and the shortest path between k and j. Okay, so this is the equation is difficult to understand, but once you have understood the idea, it's quite clear. So the overall length of P is the length of the first part of the path plus the length of the second part of the path. Okay, this is because we know that this path goes through k, but it could be the case the shortest path does not go through k. So in that case, the overall length doesn't change, and that's why here we have a minimum among the two. I hope this is clear. Now, this is a way, of course, to compute the length of the shortest path, but we want to compute the path themselves. So we are not, it is not enough to compute the length of the paths. We want to compute the path themselves. Okay, and to do it, of course, as we did for BFS and Dijkstra, we may use something called predecessor. So the predecessor of a node will be the node which comes before that node in the shortest path. Now, in the case, let me just move to my whiteboard. So in the case of single source shortest path problem, we have a single source, which is the node from which we are moving on. Then we have a graph, of course. Let me label the graphs in a proper way. So let me see. So 3, 2, 1, and 6, let's say. Okay. So in this case, it's quite clear what's going on with this node. So the last one. So the one in the bottom of my drawing. So what's going on here? Well, the predecessor of this node is for sure this one. The predecessor of this node is for sure this one. The predecessor of this node is for sure this one. There's no ambiguity. Why? Because there is one single predecessor for each node, since we are dealing with a tree. Yes, a tree from the from the source. Okay, but in all pairs shortest path problem, we may have some difficulties in dealing with the predecessor, and the main problem is that, so let me rebuild the graph. I just build above. This is 1, this is 3, this is 2, and this is 6. Now here we don't have a single source, so we may want to know the shortest path moving from this node to this node, for instance. In that case, of course, the predecessor of this node will be this one. So let me go back, change the color. So if we want to compute the smallest path from this node up to this node, of course the predecessor of this node would be this one, the predecessor of this node would be this one, and that's all. Now, what if instead we want to compute the distance among these two nodes? So let me change the color, this node and this node. Well, in that case, the predecessor of the node on the bottom of my drawing would be this one. And as you see, depending on what the path I want to get, I have a different predecessor for my destination. So while in the single source shortest path for each node we have one single predecessor, in the all pairs shortest path problem we have a single predecessor for each path. Okay, so once I know the source and the destination of my path, I can say, okay, the predecessor of the destination is this one. So if this is the case, in the single source shortest path problem we may use the property pred to deal with predecessor. Okay, predecessors. While in all pairs shortest path problem we cannot do it, of course, and we need a matrix let me call it pi to represent or to store the predecessor of J in the path from I to J. Okay, well, I don't know why I moved down there. Okay, so the idea is that so pi I, well, let me write in this way, ij store the predecessor of j in the path, in the shortest path. From I to j. Okay? So, once we have understood that a single property for a node is not enough to represent the predecessor, because we are dealing with many different sources in this problem, let me go back to the slide and say that as we did for if you remember, for Dijkstra, we handled the predecessor in the same way we handled candidate distances. And we may do exactly the same in this problem, and actually the Floyd-Warshall algorithm did it exactly in the same way. So every time this minimum takes as the shortest path the one contained in K, we may need to update the pi matrix at the K level, saying the shortest path among I and J whose greatest internal node is K, must have as predecessor for J the predecessor of Kj at the K minus 1 level. Okay, so the idea is basically the same. And let's have well, this is not let me move to the slides. Let's have an example of what's going on. So here we have a graph with a graph theoretical representation of the graph itself, a weighted graph, of course. This is the adjacency matrix of this graph. At the beginning of computation, we need to build two matrices. The first one will represent the distances, the shortest distances among all the nodes in the graph, whose internal node is 0. So basically, at the beginning of computation, we are dealing with adjacency matrix, in which we replace the diagonal value by 0, because of course the reachability of a node, the shortest path between a node and itself is the empty path, and so the cost of the empty path is 0. Okay, so D0 is built up by taking the adjacency matrix and replacing the main diagonal by zeros. Once this is done, we can build up the pi function, well, the pi matrix, which is the matrix telling us which is the predecessor in the shortest path between two nodes passing through no internal nodes. Okay, so here we have the predecessor of all the edges reporting all the edges but the ones on the diagonal, of course, which are useless from the shortest path point of view, because they are self loops, of course, and so we are reporting we are taking care of all the edges on the adjacency matrices, but the one on the main diagonal. So here we have in the adjacency matrix we are representing an edge moving from 1 to 2. So we know that the shortest path going from 1 to 2 has as predecessor for 2, 1. And that's why here we have a 1. And again, the shortest path moving from 1 to 4 as predecessor for 4, 1, because we just need to cross one edge again. So as you see here, we are basically writing in each element the number corresponding to the row in which we find the element, if there is the corresponding edge. So here we have an edge between 1 and 2, and here we are writing 1 because the row is 1. Here we have an edge between 1 and 4, and here we are writing 1 because the row is 1, and so on and so forward. Okay, so building up the first version, let's say, of pi is quite easy. More or less just like building the first version of D. Now let's try to move on. As already said, in the main diagonal of the first version of D, I'm placing all 0, and in the main diagonal of pi, I'm placing all nil, because all the edges, all the self loops are useless from the point of view of shortest path. Okay. Now let's try to compute the shortest path by allowing as internal node 1. Well, as you may see from the graphical representation of the graph itself, 1 cannot be in the middle of any path. So by allowing it, we are not changing anything. And as a matter of fact, if you look at the two matrices right now, we end up in nothing, and nothing more of what we did before. Okay, and this is it. Now let's try to go one step further, and let's see what's going on if we admit as internal node the node number 2. Okay, so right now we have a node 2 here, which is just in the middle of a possible path. As you see here, we have a path between 1 and 4 whose length is 6, as you see here, and we have reported here because we have this element which is in row number 1, column number 4. So you have a path moving from 1 to 4, whose length is 6, and moreover, in the predecessor matrix, we know that the predecessor of 4 in the shortest path is 1. Now if we allow the value number 2 as well, node number 2 as internal node, we end up in comparing this path with this path, so with the path passing through 2. Okay, and this is done by trying to move from 1 to 2, and this is the case, and then from 2 to 4, and this is the case. So we are summing up these two values, we're getting 5, and we check whether the new path is smaller than the previous one, and this is the case. Okay, so we are now able to update this value, and along with this value and together with this value we also need to update the corresponding value on the matrix of the prefixes, because we know that right now the shortest path is not the one moving along the edge 1, 4, but is the one which goes through 2. So the last step in the shortest path is to move from 2 to 4, and then we need to update this value in this matrix by writing 2. Okay. Now this is just one step, but of course we need to build D3 and D4. Now let's see D3. Here we have a problem. I don't know why this changed it 4. It should be 2. Probably I changed something the last time. However, the matrix doesn't change anymore. Okay, and at the end of the computation we we are able to provide this matrix and this matrix. These two matrices are the matrix representing the shortest path, the length of the shortest path among all the pairs of the graph, and this matrix report the shortest, the predecessor of that shortest path. So if you right now, once you have computed everything, once Floyd-Warshall have ended all the computations, you may ask me what's the path between, I don't know, let me say 4 and 1. Well, I go I try to find the corresponding predecessor in this matrix, which is, so we are moving from from node number 1, so row number 1. We are trying to reach node number 4, so we go to the column number 4, and we know that the predecessor of 4 should be 2 in the shortest path. So now we need to find the predecessor of 2 in the shortest path from 1 to 2, and we go on this way. Okay. So the predecessor of, so we look again here, we are searching for the predecessor of 2 in the shortest path from 1 to 2, and the predecessor is 1, and so we have built the shortest path. Okay, so by using the final pi matrix, we are able to rebuild all the paths among between every pairs of nodes in the graph in linear time with respect to the length of the path itself. Let me try to answer some of the questions I just received. But there is a self loop on node 2. Doesn't mean that the distance 0 of 2 should be equal to 1 because the path stay on the same node is not empty. No, as I said, if you need to decide the shortest path among a node and itself, of course the shortest path is a path of course is a sequence of edges whose subsequent edges, whose initial node is the source of the path and final node is the destination of the path. If you have one single node, the shortest sequence of edges which bring you from the source to the destination is the empty path. And so that's why we fulfill all the elements in the main diagonal by using 0. This is, I mean, much more acceptable if you think to a path in which you may encounter a loop. If you have a path between two nodes and by going through the path you may reach a loop, do you go straight to the destination or you keep going through the loop? You go through the destination, so you must try to avoid all the loops in searching for the shortest path. And that's why we are not setting in 0. We fill all the elements in the main diagonal with 0. Okay. So this is it. Now let's have a quick review of the code. This is the quick review of the code. In some sense, it really appears just like the relax step in the Dijkstra algorithm, if you remember. So here, for all pairs of nodes I and j, well, first of all we build a copy of the original matrices. Okay, this is a step of Floyd-Warshall step. So we are trying to move from the kth version of the matrix D and pi to the kth plus 1 version. So we copy then, and then for every possible path, so from moving from I to j, and by using these two for loops we are taking care of all the possible paths. We test whether the path between these two nodes, which does not go through the node k, is greater than the path built up by going from I to k and then from k to j. If this is the case, then by using k in your path, you may reach, you end up in having a shorter path. So we need to, in that case, we need to update the distance, the shorter distance between I and j, and this is done by summing up the shorter distance between I and k and j. And then once this is done, we need also, of course, to update the predecessor of j in the path between I and j. And this is the predecessor of j in the path from k to j, because we decided to move along these two paths. Okay? And once this is done, we return the MP. So this is a single step of the Floyd-Warshall algorithm. Now let's try to summing up everything in the Floyd-Warshall pseudocode. Here at the beginning of the computation, of course, we need to build up the initial version of both matrix D and pi. Okay, and we can use it. We can build up by using these two fake, let's say, procedure. You may write them straightforward. I mean, it's just not that difficult to build these two procedures. I mean, the first one is just copy the adjacency matrix and then fulfill the main diagonal by 0. The second one is just as already said, going through the adjacency matrix and test whether an edge is present, and apart from the main diagonal, fill the corresponding value, the corresponding cell with the row you are dealing with. So these two procedures are quite easy. It takes time, quadratic with respect to the number of nodes in the edge. Okay, both of them. Now, once this is done, of course, we need to repeat all the Floyd-Warshall step until we end up in allowing all the possible nodes in the graph as internal nodes. So we start with 1 and we end up with the cardinality of the nodes in G. Okay. Now, what's the complexity of this stuff? Well, if we look at one single Warshall step, we end up Floyd-Warshall step. We end up in easily understand that the complexity is quadratic. So a single Floyd-Warshall step is has a complexity which is quadratic with respect to the cardinality of V. So with respect to the number of nodes in the graph itself. Why? Because copying the two matrices are square matrices whose size is cardinality of V. So these two steps takes time, theta of cardinality of V square. While here we have two for loops, and again they are going from 1 up to the cardinality of V. So the overall cost of these two loops is theta of cardinality of V square. Okay, so the overall cost of the Floyd-Warshall step is theta of cardinality of V square. What about the Floyd-Warshall procedure? Well, the two initial procedures takes time. Again, theta of cardinality of V square. This for loop is a for loop going from 1 up to the cardinality of V, and at each iteration we are performing theta of cardinality of V square operations. So the overall cost of this for loop is theta of cardinality of V cube. So the Floyd-Warshall algorithm takes time, theta of cardinality of V cube. Okay, And that's all. It's really interesting to notice that we haven't assumed anything about the weights of edges. So this algorithm easily handles also negative weights. Of course, if they are not involved in any loops. So if a loop is a negative loop, the definition of shortest path does not exist anymore, and so the Floyd-Warshall cannot be the Floyd-Warshall algorithm cannot be applied, just like the Dijkstra algorithm. Okay, is it clear? Any question about what we saw until now? Good. So let me I don't want to go on right now because we don't have enough time to start a new topic. However, let me show you something. So let me show you something if I'm able to find it. So I prepare for you a new set of homework. Okay, here we are. We almost are there. Let me reduce all this stuff. So this is the new set of exercises for you, which is, I mean, could be, I mean, I don't think it's that difficult to be done, because I mean, the implementation of the Dijkstra algorithm is almost straightforward. Not really difficult. The toughest part is to handle the key, so the update of the candidate distance and the extraction from the priority queue. However, we have already implemented them in lesson number 6, 7, and 8. Well, better. We haven't directly implemented them because I mean you need the implementation you did by your own as a exercise for that lesson. I mean, this part shouldn't be that tough to be done. Okay, and I want to let you all the freedom to implement all this stuff as you want. So I've not prepared any framework to do it. I mean, just avoid any mess and represent nodes as natural number, and the graph should be represented as a GSSA list. So it should be quite easy to do it. It shouldn't take you more than let's say 2 hours in doing both of the exercises. If this is not the case, please let me know. We try to manage a way to do all this stuff all together. Okay. So I really want that you try to implement at least the array-based version of the Dijkstra algorithm, and then the second part should be straightforward, what we already said. So the second thing I prepare for you is the following one. Let me go to this stuff. Okay, is a set of exercises which are not really mandatory, so they are not homework. They are kind of preparation for the exam. So it could be the case that during the exam I may ask you something like well, if we have an array of n integer values and so on and so forth. So this is just a way to prepare you for the exam, and I want you to try to solve all these problems, try to find a way to answer to the questions. Okay, I mean, again, it's not mandatory. This is not part of your homework. This is only just to prepare you for possible questions you may have during the exam, which, as already said, would be oral. You will find everything below the video you are following right now on YouTube and on Moodle. I mean, they are not really they are not right now on Moodle, but I will place them as soon as the lesson will finish. So that's all. If you have any question, let me know, and send me an email, write me on Moodle. If you need to have a session to discuss, if you need to have an online session to discuss all the exercise and to ask questions about the topic we already see or what we did right now, let me know. I'm available for having conversation with you alone or together, just as you prefer. Okay, that's all for today. So thank you for the attention. I hope you enjoy the last part of our discussion. I hope you enjoy Dijkstra algorithm. I hope you enjoy the Floyd-Warshall algorithm, and in general the algorithm on the weighted graph. During the next lesson we will deal with a really related problem, which is the routing problem, which is a simplification, let's say, of the single source shortest path problem actually. But as we will deal with large graph, it could be very tough to be solved, and that's it. So thank you again for the attention, and see you the next week. Bye.